Hello, friends. Good to be with you all again. Just a warning. I have a friend that's coming to visit from Alabama that she's on her way here now, so I might have to pause the video for a second to give her some directions. So just to let you know that. You guys made it through another chapter of physics, and I think you're under a month now for graduation. Like I said, I'll be there. I'm excited to see you all for that, and just push through these last few weeks. You can do it. I'm not sure how exams work, but I think if you make an A or something, you won't have to take my exam, so that's awesome. So keep that in mind as you push through these last few weeks. Today we are going to start chapter 13. I actually haven't seen your test grades yet because I just gave Coach Reese the key. Hopefully you all got the key, and if you still have any questions, just ask him to email me or text me, and I can work out some of the problems or any of the problems you had questions with for Monday. I can do that for y'all because this will be for Friday. So yeah, I can do that for you. I just didn't want to waste your time if you guys understood everything that was going on, or once you saw the key, you understood what you did right or what you did wrong. So we're going to jump straight into chapter 13 today, which deals with the different states of matter. So we're going to deal with fluid states today, and we're going to learn how to calculate pressure. So we will do that, and then I'll give you some practice problems, and you will get to have a great weekend. It shouldn't be a long video, so you should be able to get your practice problems done, so you won't have any homework. All right, so let's get started. So look at page 300. Made it to the 300s, woo! All right, so we're going to look at the fluid states and the properties of fluids. So how does a fluid differ from a solid? If you put an ice cube in a glass, the ice cube has a certain mass and shape, right? Has a certain mass and shape. And neither of these force quantities depend on the size or the shape of the glass, okay? What happens, however, when the ice melts, its mass remains the same, but then its shape will change, right? It won't be that solid cube anymore. It'll be like fluidy, right? The water flows to take shape of its container and forms a definite upper surface. If you boil the water, it would change into gas, water vapor, and it would flow to fill to expand whatever container that it would be in, right? But the water vapor would not have any definite surface. So what we need to know basically about fluids is that fluids are materials that flow, but they have no definite shape, right? Because they fit whatever container they are in, right? So that's the main thing that we need to know about fluids, okay? So pressure in fluids. Can Newton's laws of motion and the laws of conservation of momentum and energy be applied to fluids? In most cases, you could say yes, but there are certain circumstances where that's not true. The mathematics would be really, really complicated, and even like the brightest people can't really figure that part out. By studying the concept of pressure, though, you can learn more about the motion of the fluid. So applying force to a surface that's the definition of pressure. Pressure, which can be represented by the following equation, is the force on a surface divided by the area of the surface, okay? So P equals force divided by A, okay? The force on the surface is assumed to be perpendicular to the surface area. If you stand on ice, the ice exerts on your body an upward normal force. Remember, we've kind of gone over this with looking at the different types of forces and things like that. It exerts an upward and normal force that has the same magnitude as your weight. The upward force is spread over the area of your body that touches the ice, which would be the soles of your feet, right? Because your feet are touching the ice. Okay, so if you look at figure 3.2, which is on the top right of 301 with the elephant, it helps illustrate the relationships between force, area, and pressure. So pressure is the force exuded on a unit area of surface. Similar forces may produce vastly different pressures. For example, the pressure on the ground under the high heel of the woman's shoe is far greater than that under the elephant's foot. Okay? So pressure is a scalar quantity, and the unit of pressure is called a Pascal. That is because that's the guy's last name, Pascal, okay? Pascal, however you want to say it, okay? It's 1 Newton per square meter, okay? But Pascal's a really small unit, so a lot of times it's measured in kilopascals, okay? equal to 100 PA. It's more commonly used. So if you look at 13.1, you'll see some typical pressures, that table right there on page 301. And then if you look at 303, you'll see some of the different ways that you can measure pressure, some of the different machines that you can use to measure pressure. All right, so how does matter exert pressure? Imagine that you're standing on the surface of a frozen lake. Your feet exert forces on the ice, a solid made up of vibrating water molecules. The force that holds the water molecules apart causes the ice to exert upward forces on your feet that are equal to your weight, right? What if the ice melts? Most of the bonds between the water molecules are broken, and although the molecules continue to vibrate and remain close to each other, they can also slide past one another. If the lake is deep enough, the water will eventually surround your entire body, and the collisions of the moving water molecules continue to exert the forces on your body. All right, so let's look at gas particles and pressure. Okay, the force exerted by a gas can be understood by using the kinetic molecular theory of gases. According to this theory, gases are made up of very small particles, right? The same particles that make up solids and liquids, but the particles are now, they're separated apart. That's kind of what distinguishes them as a gas, right? They're widely separated in constant random motion at high speed, making elastic collisions with each other. When the gas particles hit a surface, they rebound without losing kinetic energy. The force exerted by these collisions result in a gas pressure on the surface, okay? So they're moving really, really, really fast. That's how you can tell it's a gas too, when they're separated. And then when they hit something, that's the pressure, right? The forces that result from when they collide is the pressure. So look at atmospheric pressure. On every square centimeter of the Earth's surface at sea level, the atmosphere exerts a force of approximately 10 newtons, okay? That's just something you got to know, 10 newtons, okay? About the weight of 1 kilogram of an object. The pressure of the Earth's atmosphere on your body is so well balanced by your body's outward forces that we really don't notice it. You become aware of this pressure only when your ears pop as the result of pressure changes when you ride in an elevator in a tall building, fly in an airplane, things like that. A lot of times when I go up to Birmingham, because it's on a mountain, my ears pop. So I don't know, maybe you've noticed that too, or maybe I'm just weird. Atmospheric pressure is about 10 newtons divided by the area of 1 centimeter squared, or 10 to the negative 4th meter squared, which is about 1.0 times 10 to the 5th newton meter squared, or 100 kilopascals. All right, now we're going to look at how to calculate pressure, and then you'll be free to do some practice problems, and yeah, that will be it. All right, so look at page 302. There are 3 parts to this problem. All right, a woman weighs 495 newtons, and she wears shoes that touch the ground over an area of 412 centimeters squared. What is the average pressure in kilopascals that her shoes exert on the ground? Is A. So that's the first part. Sorry. B. How does the pressure change when she stands only on 1 foot? B. All right. Now C is, what is the pressure if she puts all her weight on the heel of one shoe with an area of 2.0 centimeters squared? All right, so going back to the usual, what do we know? We know that the force is 495 newtons. Sorry. 495 newtons. All right. Get that from the problem, okay? We know the area of A is 412 centimeters. Tells us that. Centimeters squared. Okay. Now B, we've got to do some simple calculations. So the area of B, we do know, but we don't know that we know it yet. How does the pressure change when she stands on 1 foot? So if she's on both feet and the area is 412 centimeters, just divide that by 2. And that's the area that will be of 1 foot when she stands on 1 foot. So that's 206 centimeters squared. All right, and then C, we are given in the problem as well. with the area of a high heel of 2 centimeters squared. Okay? So, we're given centimeters, but we need it to be is meters, right? Because it's over, when you have a Pascal, it's Newton meters squared. Okay, so we have centimeters. So to do that, you just have to move it. I'll show you how to do it. AA is equal to 4.12 centimeters squared times 1 meter squared over 100 centimeters. All right, squared. So that's going to go away. The centimeter squared goes away, and you're left with 0.0, sorry, I don't know if you can see me, 0.0412 meters squared. Okay, just a simple conversion. All right, let me show it to you. So I haven't done really any of the problem. I've just converted to the correct units, meters squared. All right, so now that we have that, we just plug in for our pressure equation. So we have our area in the right meter, or in the right units now, and then we have our force. So all we do now, pressure is going to be equal to 495 divided by 0.0412. All right, and that's going to give us the bottom here. Sorry, I'm trying to make it so it's not as confusing. 1.20 times 10 to the 4th Newton meters squared. All right. So that's what we get for here, but it asks us to do it in kilopascals, okay? So to do that, you just have to multiply it by 1,000 Newton meters, or divide it by 1,000 Newton meters squared. So I'll show you that too. I'm going to erase some of this. I'll just show you how to convert the to kilopascals once, and then we'll just assume that we do that for the other one. So we got 1.2 times 10 to the 4th times 1 kilopascal divided by 1,000 Newton meters squared. All right, so that's going to make those 2 Newton meters go away, and you're going to be left with 12 kilopascals. So that's A. Okay, now B. B, we have our area of 206 centimeters squared. Still have to change that, so I already showed you how to do it. So hopefully you get 0.0206 meters squared. All right, so now you just got to plug that in. 495 newtons divided by 0.0206 meters squared. It'll give you like 2.0, I think, times 10 to the fourth, but it's really going to be 24 kilopascals. All right, once you change it to kilopascals. All right. Now the last one, you do the same thing. Convert 2 centimeters squared. So the area, AC, will actually be 0.00020 meters squared. I'll plug that in. 495 divided by 0.00020 meters squared. It's going to give you 2,500 kilopascals. Okay, great. That's all we're going to do today. I'm going to get you to do 1 through 3 on page 303 for homework. You'll give it to Coach Reese on Monday morning. But yeah, I'm proud of you guys, you ladies as well. You all, sorry, being gender neutral. And I hope you have a great weekend. And as you inch closer and closer and closer towards college or other jobs or just taking a break for a little bit, whatever you feel like is right for you in this moment, I hope you found peace with that. I hope if you're looking for college, you verified your final decisions. And if not, you're in the process of discerning that. Just know that I'm thinking and praying for you all during that time. And yeah, I hope you guys have a great weekend, like I said, and I will see you on Monday. Bye.